Hello, in this lesson we're going to look at the topic mapping figures, and I'm going to give this lesson the title Mapping Figures. We're going to call this Mapping Figures. And we'll start with the definition of a regular polygon. This is going to be important. In just a few minutes you're going to need to know what a regular polygon is. This is an enclosed figure with all sides the same length. Make that a little bit smaller. Okay, and then the other important definition is line symmetry. Line symmetry is when you can reflect a figure over a line and the figure appears unchanged. And the last important definition that we will look at is rotational symmetry. This is the property a figure has when it looks the same after a rotation. For example, for rotational symmetry, if you have the letter S, the letter S looks the same when you turn it upside down. So let me take a picture of this letter and I'll show you what I mean. See if it appeared on the screen. It did. Okay. Here's the letter S. If I turn it upside down, it still looks like the letter S. So turning something upside down is 180 degrees. That's a 180 degree rotation. So the letter S has 180 degree rotational symmetry. Another example would be of line symmetry, the letter A. This is for line symmetry. The letter A can be cut in half and it looks the same on both sides. That means that it has line symmetry. So I could reflect A over this line and it would look exactly the same. It would appear unchanged. And the last word that we looked at was a regular polygon. This is when you have a figure where all the sides are the same length. So that would be, for example, a square. This is not very pretty, but a square, every side is the same length. That's a regular polygon. Or an octagon, where all the sides were the same length. Or a hexagon, or an equilateral triangle, where all the sides were the same length. Those three terms are going to be super important for today's lesson. So we're going to start with, let's fill in this blank. So down here underneath where it says notes, let's undo that. Where it says notes, we're going to fill in when you map a figure, because today's lesson is about mapping figures. When you map a figure to another figure, you are figuring out how could you transform the original figure so that it is in the exact same position as the second figure. And in just a moment, we will look at an example. Let's go ahead and look at example 1. We're supposed to figure out how could you map triangle ABC to triangle XYZ. And just looking at these two figures, I know I'm starting with the pre-image and ending up with the image that I'm pointing to. And it kind of looks like the triangle has turned around. So I think that some sort of rotation has happened. If you look at the answer choices, there are two things happening. There are two transformations happening. We have to figure out which two. So since I see that a rotation has probably happened, most likely C and D are not the correct answer because they do not include a rotation. Let's look at answer choice A. Answer choice A says rotate 90 degrees clockwise about point B. And I'm going to draw an X and Y axis, okay, around point B. So 90 degrees clockwise would put this figure, okay, so this would be A prime over here, and then the figure would look like this. So let me draw that in another color so you can see it just a little bit better. Okay, so it would swing upwards like that, and the slanted side would be over here. Okay, so that would be 90 degrees clockwise, and then if I reflected over the y-axis, you see how A prime is 1 unit away from the y-axis? It would have to be 1 unit away from the y-axis over here. That would be A prime. A double prime, actually. A and X are corresponding vertices. So A goes from being right here to being X over here. So we rotated 90 degrees, and then we reflected, but A double prime is not where X is, so that's not the answer. I'm going to erase this, and we're going to try again. So I see that A is not the answer. What about B? Okay, I'm going to rotate again about point B for letter B, but this time I'm going 90 degrees clockwise about point B. Oops, and then I am translating left 5. So let's try the rotation again. Still exactly the same. So this is A prime. This is C prime. The figure has swung in this direction. The slanted side is over here now. And this says translate left 5. So this is A prime, 1, 2, 3, 4, 5. It's supposed to be where X is. Same thing with this is B prime, 1, 2, 3, 4, 5. B and Y are supposed to be corresponding vertices. So B is the same. B is the answer, excuse me. B is the answer because if I slide this figure over 5 to the left, I'll end up in the exact same spot as XYZ. We're going to look at another example, and that is example 2. Example 2 says, how could you map FGHI to STUV? So F and S are supposed to be corresponding vertices. They go together. So F is supposed to match up with S. We're going to look at the examples or the answer choices. I think that some sort of rotation or a couple of reflections have happened. So we're going to have to see of these choices which one either has a rotation or a couple of reflections. I see reflect and reflect. Most likely C and D are not the correct answer because we would have to reflect and then reflect again, and then if you reflected again, you still wouldn't have this shape in this position, so C and D are probably not correct. What about rotating 90 degrees clockwise about point H? We're going to try that. 90 degrees clockwise about point H will put this figure over here. It'll actually go off of the chart. That's fine. We can figure out sort of what it will look like. So segment IH is down here. It's going to be on this pretend y-axis when I rotate 90 degrees. So H will still be here, but I prime will be here. Okay, so this is the short side of the rectangle, and the long side will be over here like this. Now, it might be hard for you to visualize this, but just know that I goes from being here to over here. And then we know that I and V are corresponding vertices. So if I is up here, I need it to be moved down here. So if I go 90 degrees clockwise like this, and then translate I down 4, 1, 2, 3, 4, I do not end up over here. That's a problem. So I do not think this is the correct answer. I'm going to try again. Okay, so I don't think these are the answers. I think it's B. So let's see if it's B. Rotate 90 degrees counterclockwise about point I. So here's point I. And we're going to go 90 degrees counterclockwise, which is this way, about point I. So this tall side of the rectangle is going to be on this purple x-axis that I have drawn. 1, 2, 3 is that length. 1, 2, 3 is the length of IF. So I will stay here, but F prime would be over here. And then this is 2 boxes wide, so it will be 2 boxes tall this way. And it's 1, 2, 3 boxes tall that way. It's going to be 3 boxes wide in this direction. So we have something that looks like this when we rotate 90 degrees counterclockwise. And then we're supposed to translate right 2 and down 6. So let's count from point I. Right 2, 1, 2, and down 1, 2, 3, 4, 5, 6. I and V would be in the same position. I and V are corresponding vertices, which means B is the correct answer. Let's look at example 3. Example 3 says, how could you map triangle JKI to triangle QRS? JKI, QRS. All right, so I think that most likely some type of rotation has happened, but I'm not really sure. So I'm going to try to figure this out. Let's see. Let's look at answer choice D, since it's only got one transformation. If I reflect JKI over the y-axis, I will have something that looks like this. Okay, which obviously does not map to QRS. So I know that D is not the correct answer. What about C? A reflection is a relatively simple transformation, so let's start with that. Maybe it's the correct answer. If I reflect JKI over the x-axis, then I end up with a triangle that is 3 units tall and 2 units wide, and it looks like this. And this is K, and this is I here. I prime. Okay, let's see. JKI, QRS. Well, the triangle is now turned in the correct direction. If I take point J and go left 4, 1, 2, 3, 4, and down 3, 1, 2, 3, J is in the same spot as Q. And J and Q are supposed to map to each other. So J and Q are corresponding points. C is the correct answer because if I go left 4 and down 3, these two triangles match up. All right, so on the back of my notes, this is what I have written down. When you Map a figure onto itself. That is what we're going to fill in our notes here. When you map a figure onto itself, you are figuring out, map a figure onto itself. You are figuring out how you could reflect or rotate a figure to place it in the exact same position as when you started. So on the previous examples, we were looking at how to map a figure onto another figure. Now we want to map a figure onto itself. Makes it slightly different. And this is when those vocabulary words come in handy. Okay, so you are trying to figure out what kinds of reflections and what kind of rotations will put this figure WXYZ in the exact same spot. Let's start with reflections because those are easier for us to understand. Okay, so how could I locate some line symmetry for this rectangle? How can you fold this rectangle so it looks the same on both sides? So here's my answer to that. I could cut this triangle or cut this rectangle in half. Okay, here is a line of symmetry. Okay, and that is x equals negative 2.5. Okay, so I have one answer already. I could reflect the figure over x equals negative 2.5. So if I were to put this point y on the other side, equal distance on the other side of this line, and each point z on the other side, w on the other side, and x on the opposite side of the purple line, this figure would be in the exact same spot. It would look exactly the same in the exact same position, which means this is one way I could map the figure onto itself. Why don't we look for one more line of symmetry, because there's only one more, and I know that you can identify this. Halfway through the rectangle, we're just finding ways we can cut the rectangle in half. Here's another way I can answer the question. I could map the figure onto itself by reflecting over, this is y equals negative 2. Okay? All right, and then there are answers having to do with rotations. So this is talking about rotational symmetry. Again, how could I map the figure onto itself? I could rotate the figure. How many degrees would make it look the same? I could rotate the figure 180 degrees. Now, not about the origin, because if I rotate about the origin, the figure will be in this quadrant 1, which is not in the exact same position. So I could rotate the figure, this is my third answer, rotate the figure 180 degrees, that means upside down, about this center point. So the center of the rectangle. So rotate the figure 180 degrees about negative 2.5, negative 2. And that's how you answer these questions. You're looking for rotational symmetry and you're looking for line symmetry. Example 5 says, this isosceles trapezoid is centered about the point negative 3, 2. How could you map the figure onto itself? So let's look for lines of reflection first. Here is the line of reflection. So I could reflect the figure over the line. Over the line x equals negative 3. That is one answer. Reflect over x equals negative 3. What about rotational symmetry? Is there any way that I can rotate this figure so it looks exactly the same in the exact same position? The answer is no. If I turn it 90 degrees, this figure will look sideways. If I turn it upside down, 180 degrees, it looks upside down, it looks different. If I turn it 270, it's sideways again. Okay, so there is no way that I can think of to rotate this figure and make it look exactly the same, to make it map onto itself. So this is the only answer. All right, how about example 6? Before we do example 6, let me fill in the blanks here. To find rotational symmetry for a regular polygon, divide 360 by the number of sides of the figure. Earlier in our notes, we wrote down the definition of regular polygon. That's a figure where all of the sides are the same exact length, so like an equilateral triangle, or a square, or this looks like a pentagon, no, a hexagon, 1, 2, 3, 4, 5, 6. A hexagon, a regular hexagon, is another example of a regular polygon. All the sides are the same length. Okay, so this is different because on the previous two examples, these were not regular polygons. A rectangle has sides of different length. This isosceles trapezoid has some sides that are not the same length. Okay, let's look at the square. How could you map the figure onto itself? A square is a regular polygon, so we can use this lovely nugget of information to answer that question. Divide 360 by the number of sides. This is just a trick. How many sides are there? Ding, 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 there's 4. Okay, so 360 divided by 4 is 90. So all of your answers for the rotations, for rotational symmetry, are multiples of 90. So you could rotate the figure 90 degrees. 90 times 2 is 180 degrees. 90 times 3 is 270 degrees. If you rotate 90, 180, or 270 degrees about whatever the middle of the square is, and this is the origin. These rotations will make the figure look exactly the same in the exact same position. It's just a trick. The 360 divided by 4 is a trick for answering this type of question. The other question is, what about the reflections? We could reflect what lines would cut this in half. We could reflect over the x-axis. That would cut this shape in half. The y-axis, okay? The y-axis, the x-axis would cut it in half. The line y equals x and the line y equals negative x are all lines of reflections. So those are my answers for how could I reflect the figure so that it mapped onto itself. And then the last example on this set of notes says this hexagon is centered about the origin. Here's the origin. How could you map the figure onto itself? There are many, many answers, and some of the answers we're mostly concerned about are the most obvious ones. So let's start with, let's use this trick that we just talked about. There's 6 sides in a hexagon. 360 divided by 6 is 60 degrees. So for the rotational symmetry, to map the figure onto itself, all of these answers are multiples of 60. We could rotate 60 degrees. 60 times 2 is 120 degrees, times 3 is 180, times 4 is 240, 60 times 5 is 300 degrees. All of those about the origin, because this is centered about the origin, about the origin. That is very messy. Okay? And then what about the reflections? The y-axis divides this in half. The x-axis divides it in half. Okay? We could reflect over the y-axis. The x-axis. There are other lines too. The only other one that I'm super clear about what it is line S. Line S happens to be labeled on the figure, and it divides the shape in half. So reflect over line S. Two practice questions. Practice question A, or 1, excuse me, you may want to pause the video and answer the question and then look at my response. Same thing with question 2. I'm going to go ahead and answer the question though. Practice 1 says, how could you map triangle OTP to triangle MNY? For me, I see that the figure has rotated around. It looks like it's not in the same, facing the same direction anymore. So there's a few questions or a few answer choices. There's one answer choice that does not have a rotation in it. So most likely answer choice C is not correct. We're going to cross it out. What about the other answer choices? How about A? Let's rotate 90 degrees clockwise. So we're starting with OTP because it's written first. OTP is the pre-image. We're starting with point T. Okay, so let me draw a brand new X and Y axis where point T is. And 90 degrees clockwise would put this figure over here. So the short side, instead of being on this axis, the short side is going to be on this axis here. Okay? Instead of being on this axis, this long side, 1, 2, 3 units tall, is going to be over here. Okay. Now, that kind of looks like this figure over here. 90 degrees clockwise, we've done it. Okay. This is O, and this is T prime, or excuse me, P prime, O, T, P. Let's see if this works out. So we did the 90 degrees clockwise. That seems to be correct. What about right 6? 1, 2, 3, 4, 5, 6. O and M are supposed to match up, so we know that A is the correct answer. Practice question 2 is the last one. It says, how could you map the figure onto itself? And I see an isosceles triangle. That means 2 of the sides are the same length. If 2 of the sides are the same length, there is some symmetry happening, some line symmetry, which means we can cut this triangle in half right there. I didn't draw it very well, but one of the answers is reflect over the line x equals 3, because we have line symmetry here. This line that's drawn on the paper, y equals 2, that line is just there as a distractor. It's just to distract you from what's happening. That is not a line of symmetry. The other question that I could ask you would be, do you see any rotational symmetry? Is there any number of degrees that you could rotate this figure so that it would look exactly the same in the exact same position? And the answer is no. So for example 2, or for practice 2, there's only one answer, reflect over x equals 3. Thank you so much for watching.